we we started. Um, let's see. So in previous segment, we introduced the concept of the equation of tangent plane to a level surface, and here the key is to observe that the gradient of this function for this level surface is indeed the normal vector of the tangent plane, or actually the surface itself. So that is how we are able to write down the equation of tangent plane. Now we want to have one example to illustrate the idea of setting up the equation of tangent plane, and we want to point out uh, this is this might be well, this is a very typical question people would see in many applications. All right. So first of all, we want to point out to find the equation of tangent plane to the surface given by, well, here the surface is given by this equation below. All right, at the point 2, 3, 3 over square root. And we want to first point out the, maybe we should write it down. Note, we want to formulate the, we can't really say this is a graph of function, right? This because it's hard to tell what kind of function will give this surface. So we want to formulate this surface into a level surface. So we can use the information we got here to write down the equation of tangent plane. All right. So what is the function capital F for us to construct the level surface? And here we should note we usually would just write everything that involves the variable and we move them to the left. And then how about the 13? Well, we can move the 13 to the left. So note 0 level surface, which is setting this everything for the function capital F to 0. The 0 level surface is this equation. So we know that we're doing the right thing by setting this capital F as the function to generate the level surface. So the original equation okay, and we also want to, so this is node 1, and node 2 is this point actually on the level surface or actually on the surface? Well, we can check it, right? So here we should point out um, x is 2, y is 3, and z is 3 over square root. So let's see, because x squared plus z squared times e to the y minus x is 2 squared plus z is 3 over square root e squared times e to the y, which is 3, minus x, which is 2. It's 4 plus 9 over e times e. So this is 4 plus 9, which is 13. So yes, this point is actually on this surface. Okay, so with this, so we should make the claim. So this satisfies this equation, so it will be on this 0 level surface. for this function. So now what? Now we need to have the gradient vector. What is the gradient vector? Again, three partial derivatives, right? So partial f partial x, emphasize, partial f partial x is 2x plus, well, z squared partial e to the y over x, partial x. Well, yeah, let's keep it. So partial 13 partial x is 0, for sure. We don't have to carry it. And then for the second one, x squared partial derivative with respect to y, which is 0, plus z squared partial y, and then minus 0. How about the last one? X squared partial derivative with respect to z is 0, plus 2z e to the y minus x, minus 0, right? So what this is relatively easy to compute because we gotta use the chain rule, and the chain rule is e to the y minus x, and then we take the derivative y minus x with respect to x, which is -1, right? And for the second component, z squared times essentially the same thing, but we have e to the y minus x, and then we have to take the derivative y minus x with respect to y, which is the positive one. So there's a little bit of difference, and this is what we have. Okay, so now we have to compute the gradient of capital F at the point 2, 3 over square root e, which is 2 times 2 plus z squared is 3 over root e squared times e to the power 3 minus 2 and times -1. And for the second component, we have 3 over 30e squared times e to the 3 minus 2 times positive 1, so we don't have to multiply. So 2 times 3 over square root e times e to the power 3 minus 2. So what do we have? We have 4 minus 9 over e times e. And for the second component, we have 9 over e times e. Last one is 6 over square root e times e. So this is -5, 9, and 6 times square root e. So this is a normal vector. And then the equation of tangent plane is, remember, gradient of capital F dot with the point, right? X minus 2, y minus 3, z minus 3 over square root e equals 0. So that is -5 times x minus 2 plus 9 times y minus 3 plus 6 times root e times z minus 3 over square root e. There. So this is our equation of tangent plane for this surface at this given point. Okay. So one thing we really want to point out, which is how we look at the equation of tangent plane. And there are two different scenarios, right? We said this is the one scenario, this is for the level surface, but can we convert the graph function? Z equals f of xy into level surface and set up the equation of tangent plane in this so-called universal or generic formula that we just discussed? The answer is yes. The answer is yes, but how do we do that? Let's just formulate it here. Note, we can set, right? We can write the level surface to be for the function capital f of x, y, z. Now with this z inclusion, what we can do? We can do this. Then the zero level surface, zero level surface as equation of tangent plane and its normal vector is then I think it is negative because the normal vector n is obtained by the gradient vector for capital F, right? So this is negative partial f partial x, negative partial f partial y, and a positive 1. So this is called the upward normal. You can also write this level surface capital F as f of x, y, z, not f, y, z, little f only depend on x, y. Okay, and then the gradient vector of capital F is giving us a normal, which has partial f, partial x, partial f, partial y, and then negative 1. So this is downward normal. Okay, we will talk about some examples in the next video series. But it is very, very, very important to see how we unify the concept of tangent plane to this surface, and it's going to be tested in quiz and test.